Welcome to Lab 8. This lab is all about memory allocation, and we'll take another look at structs to give you some more practice with using data structures in C, so slightly more complex data structures. So in particular, we want in this lab to use memory allocation strategies for high performance, which is often something you need to do when you're dealing with large amounts of data and you have to allocate, and in particular you want to resize certain things in your program. So resize data structures in your program. So that's what we're going to focus on in this lab. So the first thing I'm going to do is just grab the archive that's shown on the web page for Lab 8 and get that archive file and then unzip it. ZXVF will unzip my lab.tgz file, and what this creates is a directory 8, and you should git add and git commit and push it as usual. But let's look at directory. In this lab 8 directory, there's a make file for you to use, and there's also two files. One is a test program, test.c, which contains a main function, and the header file, pointarray.h, which contains the main data structures. So we're going to use two data structures. One is called point_t and the other one is called point_array_t. So this is an array of points where we store the length. And this is a point data structure which stores three doubles x, y, and z. And the objective of this lab, in Lab 8, what we're trying to do is implement these functions that are in this header file, and we're going to implement them in two different ways. The first way is a already fast way to implement it, and then the second method in task 2 of implementing the same functions will be even faster. Okay, let's look at task 1. Task 1 is about resizing arrays using a function called realloc. So we've seen malloc before. This particular task will introduce you to realloc and try to convince you that using realloc will improve your performance when you have to do extremely large resizes of your data structure. So if you have to do it often, or if you do, if you're unsure of the ultimate size of your data structure or your array, and you're resizing it, realloc can be very useful. So that's what this first task is about. So there is a structure called point. Point stores three numbers. There are three doubles. And then there is an array of these structures. So notice that each element in this array point t pointer, is an array that consists of several of these points. And we store the length of our array in, so the length of the array is stored in this structure, which is called point array type. So point_array_t, which I will say out loud as point array type. And this would be the point type, or point_t. Okay, so the main task is to implement these four functions, and that's it. So it's fairly simple. So these are the four functions we need to implement, and once you implement that, you're done with your task 1. The functions look somewhat similar to functions we have seen before, but you should be careful. They're actually somewhat different. They don't ask you to allocate certain things, but they do expect you to allocate other things. So in particular, when it passes in a point array point array type pointer. This point array type pointer is assumed to be allocated already, and what we are doing here in init, the init is just making sure that everything is set up right, that it's length 0, and that the array of points is actually empty. Now the main things, so the first two functions, init and reset, are quite simple. The reset function as well will take a point array type, and what it will do is make sure that its array is empty. So basically it will make sure that the length is 0, and that the pointer that has the array of points is actually freed. The meat of task 1 is in append and remove, and both of these functions are where I suspect you'll spend most of your time. And in this case, what you're doing is you're taking a point array type, which is the first argument, and then a point type, which is p. So this is a struct containing those 3 doubles. This is the struct containing the array of points and the length of that array. And what we're doing is append, point array append is going to add at the end of this array and make space for a new point. So we want to append a point. And the usual way to do this is to allocate a new array of a larger size, and then copy over the old array into the new array which has size 1 larger. And actually I'll show you that code in a second. And you free the old array that you had, and you make sure that PA, this point array type, is now pointing to the new array that was just allocated using malloc. So if you use malloc, that's the only thing you can do. Allocate new memory, copy over what was in the old array, deallocate or free the old memory, and then make sure that the new memory is what is being pointed to in point array type. Right? So that's what you can do in malloc, and I'll show you code that does that. And then the last thing is remove, which takes a point array type, and then it removes one element from the array. The important assumption here is that the order of points in the array can actually change. So we don't really care if after we remove an element, whether the array has the same elements in the same order. It could have the elements in a different order. And that gives us the ability to do what's called an unsafe remove. And so that's a second sort of point, is we could get performance by making some assumptions about the data. And we'll look at that as well. So first, let's just look at how to implement append with just malloc, and then I can explain to you how realloc works, and then we'll look at how remove can be made faster as well in order to save space or allocation and avoid resizing the array when you remove something. So let's look at an inefficient way to implement the function point array append. So in this implementation, I'm not going to use realloc, which is what you're supposed to do, but use malloc instead, which is what we learned to do in the earlier lab. And so point array append takes 2 arguments, a point array type and a point type. And where the idea is that the new point is being appended to the array that's stored inside the point array type. So let's take a quick look at these 2 data structures again. So point array type and point type. Let's just look at these 2 data structures. So point array type has a length. That's the length of this array, and this array is stored as basically this is a pointer to this array of points. So it has multiple points, and each point is just these three numbers, right? So we're given a point array type element. So we're given a struct of this type, and which points to an array, and then we're given a new point of this type, and we ask to append it at the end of this array points here. Okay, so I hope that's clear. What we are trying to do is clear. So let's go back to this implementation. So in these lines, I just check that everything is kosher, everything is allocated, there's no null pointers. If the points array was empty, then I should start with at least one point, right? So this may be the first point that I'm adding, so that's why I malloc. And I set the length to 1. I'll actually copy the point into the array a bit later because it's the same for both cases. So whether the array was empty or not, we always want to copy in the new point. So if the array was empty, we make sure that it's now containing at least one point. If it was not empty, so there was already an array of some length, then we create a new pointer, and notice that the length of that pointer is a previous length plus 1. So we added one extra space, so the size of points t, which means we added space for one extra point, and we allocated that, and we've assigned it to a new pointer which is of type point underscore t. And then I have a for loop here that just copies all the old points into the new memory location. So the old points are in PA, pointed at points, and the new memory location is new P. I just copy over all of the points, and then I can free the old location because I don't need it anymore. I make sure that the array that the point array type is using now is contains basically the new array that I allocated of one extra point. And then the last thing we do is whether we have a new array which we just allocated of length 1, or whether it was one extra element and we copied the rest over. The last element has to be copied over, so that's in px, py, pz, and we copy it over to the new pointer. So what I've done here is just use an extra line here just to capture the it just makes it a little bit easier to read to have these 3 lines rather than have this whole thing repeated over and over again. Makes it hard to read. So I just took the address of the last element and I assigned it to this temporary variable, which is a pointer, so it's going to change the location with these new values that I just passed into this function. So this definitely works. It works as an append. The problem with it is it's kind of slow, as I'll show you when I run it. So I'm going to use the testing program, and I've compiled the program that uses the implementation of append that uses malloc, and I've called it T0 because it's not even a task for you. It's just kind of what you would do if you didn't have access to realloc, which is what your task 1 is about. So let's just run the malloc version of append, and you can see as it's running here that as the lengths become larger, it takes longer and longer to append, because every time it has to copy over everything and then add one element, and then you add another element, it copies over everything to a new location and then adds another element, and so on. So what you see here is the lengths become larger. As the lengths become larger and larger, you can see that the append time, so this is in microseconds, becomes larger and larger. So as there's not even that much data, right? It's just 32,000 elements, and it's already taking 2,800,000 microseconds, which is astonishingly slow, given that C is supposed to be a very fast programming language. And so what happens if you compare it to T1? T1 is what you're supposed to implement, and if I run it, it just runs almost instantaneously. As you can see, what used to take that many microseconds now takes these many microseconds. So there's a huge difference in performance just by using realloc instead of malloc, and that's what you're going to implement in your task 1. So instead of using malloc and copying over every time we want to resize the array, we're going to use realloc, and realloc takes a pointer. So notice that this is the C way of saying I don't care what type of pointer it is. Void pointer says I'll take a pointer of any type. And so this is kind of a cheap way of getting polymorphism, or having the types be generic, or where the type doesn't matter. This function works for a pointer of any type. And what it does is it says, oh, there's a new size. Maybe if I want to increase the size, for example, I'll look for whether I can add some extra space at the end of this pointer, in which case a pointer doesn't change, but the length changes. If it cannot find enough space for increasing the size, and what it does is it returns a new pointer. So it always returns a pointer. Sometimes returns the same pointer you passed in. Sometimes it returns a new pointer and copies over everything because it was unable to resize your pointer. So this is another gotcha you should be careful about. Always make sure that you're keeping track of the output of realloc and assigning it to your pointer that you're saving in pointer array type, because that pointer can change. It doesn't always just resize it. Sometimes it has to create a new allocation, copy over stuff, just like we did. But if it can't find space, it's going to increase it. In the worst case, if it can't find space, it's going to do exactly what we did in the demo I just showed you, which is copy over everything and allocate a new space. So let's just look at what realloc is doing, and I'll use an example to go through what realloc is doing. So I'm just going to use this spreadsheet to give you kind of a cartoon picture of what's going on when realloc works. So this is supposed to be a picture of the memory, and this is all the memory that you have, and let's assume that this initial part from 2, and this 2 here is a pointer. So it's just the memory location, which each of the memory locations has a number. So in this case I'm just calling it 2, 3, 4. In reality the memory addresses will be in hexadecimal, and it'll be from 0 to 2 to the 64, or 2 to, depending on your machine word size. So in this case we're just going to make a simple pointer with just a number, and each number is a number to this location. So that's what a pointer is. It's just a number that tells you which location to look at. And let's assume that from 2 to 8 the memory has been allocated already, and also from 18 to 21. So this has been allocated before your program even starts. Something else in the computer has already allocated some memory. Somebody else's program might be running at the same time. They are using memory as well, so you don't have exclusive access to memory, right? So it's not going to be like totally empty. So the first free space of memory is in this pointer 9. So let's say that we ask for space, and we have a point array. So a point array can have many points. Each point has 3 numbers, right? So 3 numbers, x, y, and z. So we have to start somewhere. So let's start with a So I'm just going to annotate here what the struct looks like. So we need space for at least one point, which has x, y, and z. And so we need to put, and we initialize it with some value. So let's say it gets 3.4, 2.6, and 10.4. So now notice what has happened is we've allocated some memory. So let's change the color so that you can see that this is now newly allocated memory. It's taken up, nobody else can take it unless we free it. And now we have one point stored in memory, right? We have an array of size 1. And now what happens is maybe we resize it. So when we resize it, if we do a malloc again, then we'll have to copy this over somewhere else. So instead, if we do a realloc, what it does is it pretty much looks at this space here. So this one is allocated, 9, 10, 11. It tries to see if there is, if you want one space for one extra point, it will say, oh, can I actually extend this memory, this yellow colored memory, by one extra point? And remember, a point has 3 doubles, so we need enough space to put 3 doubles. I'm cheating a little bit here and saying that the double fits in one word, one memory location. It doesn't really. It takes up more than one memory location, but let's just assume that the double can fit there for the purposes of this cartoon. So we can now allocate a new point and add it to the array. So this is element 0 of the array, and this is element 1, and we're going to add some, so there's a new array here. And notice that we just extended this, so I can now get this additional point added in, and now there are 2 elements in this array. And we can do this again, so we can resize this array again. We can create x, y, and z, and add 6, some numbers, it doesn't matter what they are, some 3 doubles. And notice that now if I want to allocate another point, I can't do it because this memory location is taken. So if I ask realloc, hey, give me space for one more point, it'll say, actually, I've kind of run out of space here. So what realloc is going to do is going to look for another space. So now it needs space for all of these, plus it needs space for one extra point. So what it's going to do is it's going to move it over here to this new space, and now it has space to resize it by one extra element. So it's going to say, oh yeah, here, go ahead and add the extra point into this space now. And again, I'm just adding some random numbers, but this reflects a new point. And now if you see how many elements there are, there's 1, 2, 3, 4 elements. And now maybe there is more space, so if I want to resize it again, it doesn't need to do the expensive allocate a new memory location and then copy everything. But notice that after the fourth call to realloc, the pointer changed. It changed from 9 to 22. So the pointer can change. It just tries to give you space as much as it can without creating this sort of copy and allocation of a new space and copying it to the new space. So hopefully this cartoon kind of helps you understand what realloc is doing and how memory is manipulated by malloc and realloc. As an interlude, let me just say that this task 1 especially refers to the fact that array structs can be allocated on the stack. And in fact, that's how, if you look at test.c, that's what it does. It creates a variable and then passes the address of that local variable to these different functions. And if you are unfamiliar with what the stack or the heap is, I would recommend you go back to Lab 3's video lecture and look at the section about stack and heap allocation in C. The other idea we're going to use to speed things up in task 1 is when you want to remove an element, we are actually going to reuse that space right away. So let me just explain to you what an unstable remove is from an array by using the same example that we used before to explain the realloc. So let's say that we have this array. So notice that this is the first element. This is the second element. Each element is a point type. So it has these 3 doubles. And so it has 1, 2, 3, 4 elements. And now we have a function which says remove an element from a certain index. So let's say I wanted to remove index number 1. So this is index 0. We want to remove index 1. Now, one thing we could do is we want to remove that index. We would want to maybe copy the whole thing over so that there is no gap in the middle of the array. But that's kind of, again, expensive, like we saw with the malloc case. We don't want to make these big copies from one memory location to the other. It just makes everything too slow. So instead what we do is first thing we do is we say, hey, we know that the length of the array is going to shrink by 1. So where there were 4 elements before, now there's going to be 3 elements. And the other assumption we make is we just have an array of points. We don't really care what's in the first position of this array, what's in array 0. We don't care whether they're in any particular order. That's not always going to be true. We're going to make that assumption. In this case, it's just a collection of points, and the order of the points in the array doesn't matter. So that's an important assumption we're making to make things run fast and use this so-called unstable removes strategy. So we want to get rid of this array index 1. So we want to get rid of these 3 numbers, 5.4, 2.1, 19.3, right? We want to get rid of these 3. So instead of just deleting it and leaving an empty hole in there, what we're going to do is actually take the last element of the array, and we're going to take a copy of that last element of the array, and we're going to move it over here. So now what we've done is erased what was there in position 1 and just replaced it with the last element. And now what we're going to do is we don't really change this memory location, but we shrink the length of the array by 1 element. So notice that what I've done here is effectively said that the length of the array is now 1, 2, 3 elements, and this is no longer part of the array. It still has those values, but we don't care. It's considered to be unused. So if I resize it, for example, I can realloc it and put new elements into that space. So what I've done is created a gap and then just shrunk the length by 1 and reuse that gap to store what was previously at the end of the array. So that's an example of how unstable remove works. So task 2 is actually a fairly straightforward extension of task 1, and the idea is actually very sort of simple and intuitive. The idea is that what we've been doing in task 1 was actually every time we wanted to append one element, we would extend and call realloc with the length plus 1, right? So every time we would say, hey, realloc, give me space for one more point. And then we would come back and append something else. We would say, hey, give me space for one more point. And so every time realloc would be extending the space it is asking for from the system by exactly 1 point. So basically enough to cover 3 doubles, right? This one point has 3 doubles. So instead, what we can do is we know that it's gonna be called, probably it's gonna not be the only time it's called append. Append is called many times. So what we're gonna do is sort of say, hey, let's just reserve a bunch of space. It's not the length of the array, because the length of the array still might contain 5 points. But when we ask for more space, instead of just allocating one extra point, we say, hey, let's plan ahead, and maybe this person is going to call append another 5 times. So let me just add some extra space, and I don't have to realloc every time and ask for one extra point. I'll just pre-allocate space for some number of points, and that way the next time it appends something, it's going to say, hey, do I really need to call realloc? Maybe I've already allocated enough memory, and I'm just going to give this append, which needs one extra space for one extra point. I'm just going to give it the space I reserved already from before. So that's the idea in task 2. It's fairly intuitive. Idea is don't just realloc one element at a time. Just reserve a bunch of space, and then every time it asks for more space, if it's already available in the reserved space, then you don't need to call realloc. So task 2 implements this very simple idea. And if I'll show you how it runs as well. So if I do make T2, and so if you remember, T1 was already fast, T0 was considerably slower. So if I run T2, it's even faster. It's an order of magnitude faster than T1. So you can see here, T1 takes 3,000 microseconds, whereas T2, which is task 2, which includes this pre-allocation strategy, is super fast, right? It just takes 782 microseconds. This is amazing. So we went all the way from 2,800,000 microseconds all the way down to 782 microseconds, all with this sort of simple intuitive idea. So it's you can see how we can make things run blindingly fast and do things like write computer video games that are responsive and have a high frame rate. We can do sort of machine learning on very large amounts of data, all by using these kinds of ideas, computer science ideas that speed up processing by using sort of these clever ideas and implement them algorithmically. And finally, for this task, I want to take this opportunity to show you a very useful tool to draw graphs. We've been emphasizing drawing pictures, drawing graphs, and quantitatively showing the difference between the performance with a slow strategy like using malloc versus using realloc. It's sometimes nice to see it graphically in front of you. So if you run, for example, if I run T0, which is the malloc one, right? This is not something you're implementing, but I just want to show you. I can save the output of T0 to T0.dat. It just contains those timing results. So, right, what T0.dat contains is just the number and the length and the time taken in microseconds. And in the same way, I can do T1 to T1.dat. It might be, so you can see it runs pretty fast. And T1.dat again contains just the same information. For each length of the array, how long did it take to append those many elements? Okay, so let's say I wanted to graphically view these two. You can copy paste this information into a spreadsheet and look at a graph. In order to do this easier on without using a spreadsheet, there is a program called gnuplot, and gnuplot is a plotting graph drawing program, and it has a very simple kind of programming interface to it. So if you have like these data files like t0.dat and t1.dat, we can take these data files. So actually when the test.c printed it out, it actually did it in a clever way. And this marker here is a comment for gnuplot. So it'll just ignore this line. It'll just look at these numbers and read in these numbers. And notice that this last line again is just marked with this comment character, the sharp. So when we want to load it into gnuplot, it'll just ignore those comment lines and just take the raw numbers. And the idea is to plot a graph which shows us the comparison between the malloc strategy and the realloc strategy. So I've written down a simple, this can be typed in. So when you type in gnuplot on the command line, you can actually say set terminal png, set x label length, and so on. But instead of wasting time here typing in all of the gnuplot commands, what I've done is I've created a file which contains all the command, and then I can call gnuplot minus c t1.plot. And what this is doing is comparing the malloc strategy with the realloc strategy. So showing you how much better just task 1 does compared to using malloc. And as you can see, what we've done is set the output to this t1 underscore append.png. And when we open this file, you can see that this curve, so this I put it in a log scale because the malloc is so much slower than realloc that it's hard to see if you don't put the y-axis in using log, because log essentially makes it possible to look at large numbers using a reasonable scale. So that's why I use log in this y-axis. And it goes sort of, you can see the massive difference between the malloc and the realloc. The upper curve is malloc and the lower curve is realloc. And going back to the comparison, also you can compare realloc with the pre-allocation strategy, and I wrote another plot file. So t2.plot, and again it's mostly the same thing, it just produces a different output file, t2 underscore append.png, and again it uses a log scale for the y. And then one thing I forgot to mention, so all this is doing is saying plot that data file that was just the output of test.c, and it's using the second column, which is the length, and the third column, which is the time taken for append. And the same for the output of t2. So t2.dat contains the output of doing the pre-allocation strategy, task 2. And again, it uses the length and the output, the number of microseconds taken for append. And so it's comparing the realloc and the pre-alloc strategy. Lines points is just a style. It says draw a line between the points, but actually mark the points with a dot. So when you run this t2.plot, it says cannot find t2.dat. That's because t2, we didn't actually produce it. So when I run it again, I can do t2 append.png, And now if you look at it, the improvement is not as drastic, like it's not so much of a difference, but it's still, you can see it's still relatively a lot faster. The upper curve is using realloc, the lower curve is using the pre-allocation strategy with realloc. So I mean, mostly this thing is here to show you that using gnuplot is cool and lets you draw nice pretty graphs very easily. You don't have to go through a spreadsheet and use that. It also lets you draw different functions very easily, unlike a spreadsheet. So you can say, hey, does this look like a linear growth or a cubic? Does it match a cubic function? Does it match a linear function? And so it's nice to use gnuplot to plot functions and compare it to real data as well. So I hope we can enjoy using gnuplot. I certainly do. And you can use it to plot all, lots of different kinds of scientific data.